Alright, well, this is Mr. Lee. In this video, we are going to go over 1.4 reference frames. Alright, so I want to start off by going over a couple of examples, and just know that this does require a little bit of imagination. That little bit of imagination will definitely help us with the understanding of reference frames. So let's begin. So let's say that you are just standing out there in the hallway. So I'm going to just represent you with the face, right? So this is you standing in the hallway. And on the other side, you see a friend, right? So you see a friend. So we'll call yourself A, and we'll call this friend B. Okay, so let's say that you are standing still. So your velocity here is 0 meters per second. Okay, so according to you, you are not moving, which is very important. And according to you, if this friend is coming towards you, let's say the friend has a velocity of negative 10 meters per second. Okay, what this means is that you observe the friend coming at you at negative 10 meters for every second. Okay, all right, so let's add to that. What if you yourself, you were not standing still, but your velocity was also at 10 meters per second, okay? And the friend was also walking with the same velocity of negative 10 meters per second, okay? So one more time, we're gonna go over the idea of according to you. And to show this, I'm going to draw a dotted line, okay? So that's gonna be our main focus. So according to you, how fast is a person moving? Okay, so we know that the person is actually moving at negative 10 meters per second, but that negative 10 meters per second is actually in reference to something that is stationary, okay, such as the room around you, or let's say the earth, right? So according to that point of view, they're moving at negative 10 meters per second, which matches what we discussed up there, right? So in the previous example, because you were the one that was not moving, according to you, your friend was moving at negative 10 meters per second. Okay, so if we take a look here, the idea is now you're no longer stationary, but you're actually moving. Okay, and so if we think about this, logically first, if you're moving forward at 10 meters per second and your friend is coming at you at negative 10 meters per second, okay, what you're going to be doing is you're actually going to see your friend approach you or reach you at a faster time. So for example, in this previous example here, right, let's say the friend takes, let's say, I don't know, 20 seconds to reach you, okay? In this scenario, if you're both moving towards each other at the same velocity, we can expect the new time for your friend to reach you to be cut in half, okay? So this is because you're moving forward, but the whole idea of frame of reference is we don't actually view ourselves moving forward, okay? And this is what we call the observer. The observer is said to be stationary. So instead of saying that you are moving with 10 meters per second, it is more accurate if you are the observer to say that you're moving with a velocity of 0 meters per second, and instead the friend is moving with a velocity of negative 20 meters per second. All right, let's try another example. So let's say you and your friend, okay, once again, so this is A and this is B, okay? You and your friend are moving, I don't know, you're both walking, right? So let's say you have a velocity of 5 meters per second and your friend also has a velocity of 5 meters per second. Okay, so let's put this into perspective one more time. This 5 meters per second is in reference to something that is not moving. And in this case, because both of you are moving, you don't see each other moving for 5 meters per second. This 5 meters per second might come from another observer over here, right? We have this person over here. This is person C, or maybe the earth itself, right? Or the room that you're in. So the room that you're in is not moving, so the room or the earth around you, the velocity is 0 meters per second. So according to anything that is stationary, you're moving with 5 meters per second. But if we were to look at each other, right? So you are moving with a velocity of 5 meters per second, and your friend is also moving with a velocity of 5 meters per second. But remember, the frame of reference, we always make the observer a stationary observer. Okay, so if you, the observer, are actually moving at 0 meters per second, okay, how fast would your friend be moving? So now we got to think about this. If we were to do a dot diagram, right? So let's say these are the dots. So here is time 0 seconds, and at time 1 second, okay, we like drop a piece of paper, and at 2 seconds we drop a piece of paper, and 3 seconds, right? And so these are equally spaced apart because you're moving with constant velocity. And so if we were to do the same thing with your friend would also be dropping the pieces of paper at the same exact positions. So what this example here is to tell you that if both of you and your friend are moving with the same velocity of 5 meters per second according to a stationary observer, okay, when you and your friend are walking side by side and you look over, you can say that both you and your friend are not moving at all because you're matching the velocities. And you might be thinking to yourself, whoa, Mr. Lee, like that doesn't make any sense. Like when I walk down the hallway, I know that I'm moving. And if I'm walking next to my friend, I know my friend is moving. You can't say that our velocity is 0. But remember, this idea of frame of reference is always in contrast with something that is not, with something that is stationary, right? So when you're actually walking, try not to imagine that it is you that is walking through the world, but rather the world is moving past you, okay? And like when you're walking in the hallway, you see the hallway moving towards you, okay, which is a really bizarre idea. So let's think about it like this. So let's say this is you, A, and let's say this is a wall, okay, that you're walking towards. If you are walking towards the wall with 5 meters per second, okay, this 5 meters per second is according to a stationary object, okay. Now, what if we just change the frame of reference? Right? So instead of saying you are walking towards the wall with 5 meters per second, if we assume that you are a stationary observer, okay, now you're not actually at rest, you're actually moving forward, right? But if we just change the frame of reference so that you are a stationary observer, it's as if the wall is actually going towards you. Whoa, isn't that crazy? So in the real world, right, we are walking towards the wall, but according to the frame of reference, you can actually shift that frame of reference and say that you're not walking towards the wall, but rather the wall is coming towards you. Okay, that is if and only if we consider you to be a stationary observer. And that is pretty wild. All right, so with that being said, there's a couple of examples that we can do. So let's go over the example problems. We'll start off with just a two-body system. All right, and there's a couple of notation that we need to work on. All right, so let's say we have a teacher. We'll just use the ABC system. So here we have person A, okay, and for this problem, person A will actually be at rest, okay, according to our stationary walls, okay, and let's say we have up here, we have person B, okay, and down here we have person C, all right, and this is what we know. We know that person C has a velocity, okay, of 2.0 meters per second. Now, watch what I do with the subscripts. So the subscript notation, we're actually going to use a comma, and we're going to put 2 letters down. So the first letter that comes after the variable is the object, and in this case, it is person C, comma, and whatever comes after the comma is the observer, A. Okay, so if I were to include this here, this would be the velocity of the observer, of the object according to the observer, all right? And you are the observer, so A. All right, now let's do the same thing, but for B. We'll have B equal to 3.5. So it'll be the velocity of the object, which is B, according to the observer, A, which is equal to 3.5 meters per second. All right, so here we have our scenario. And in the scenario, because B is faster than C, according to A, it's important to know that B will always be in front of C. Okay, so if this is the path that they take, person B will always be in front of person C. Okay, so knowing this, we should be able to actually come up with the relative velocities using our observer and object notation. So, for example, here we have VB of A is equal to 3.5. But if I were to ask you, well, what about object, let's say object C, according to object B? So if we think about it, right? So if we have the velocity of object C according to object B. Remember, the observer is always considered to be the stationary observer. And so if person B is always going to be ahead of person C, what is going to look like is that person C is actually moving behind them, like away from them. It's kind of like when you're in a race and you are like gaining the lead and everyone else behind you is getting further and further away. So the perspective would be because you're considered to be quote unquote stationary, in order for you to get the lead, the others have to be moving away from you. Okay, and so if we take a look at here, we can figure that out in terms of the I guess a little bit of logic here. Okay, so if person B is traveling 3.5 according to person A, and if person C is moving with a velocity of 2.0 according to person A, okay, so what this means is that if we were to look at these two numbers, we can say that person C, according to person B, is actually moving 1.5 meters per second, but they're going behind them or backwards. You see how we did that there? Now, what if we were to flip the point of view, right? What if we are looking at person B according to person C? Well, in this case, if person C is stationary, okay, and person B is in fact faster, it's just going to look like person B is just getting further away from you. And that difference will be 1.5 meters per second, right? And this is positive. And you see here how this is the reverse in terms of sign. So the way that we know that is if we take a look at the subscripts, if your subscripts are just flipped, it'll be the same exact magnitude, but a reversal of sign. All right, so let's do a practice problem, and I'm going to show you a formula that we can use in order to solve these trickier situations. All right, so let's scroll down. Okay. So let's say we have person A right here, okay, and we have person B down here, and we have person C up there, okay. And in this situation, person A is stationary, okay, so this is stationary. As in, according to us, they are not moving at all. The velocity of, oops, and here are the nodes. The velocity of person B according to person C is equal to 0.3. And we can say that according to, so velocity of person B according to person A is equal to negative 0.2 meters per second. All right. So it's important here to know that C is the faster one. Compared to B. Yeah, and I'm just making sure. The reason why I hesitated is I was looking at this, right? So what this says is that person B, according to person C, is moving 0.3 meters per second, right? And I just had to quickly remind myself that this is in fact positive, and these people are going to be moving in the negative direction. So according to person C, person B will always be moving to the right or quote unquote away from them. So person C is in fact faster. All right, so here we have our scenario, and if we can come up with a formula, okay, a method of some sorts. So here I'm going to give you like blanks for subscripts. So we have the unknown velocity that we're looking for, okay, and we have a subscript, comma, and a subscript, okay, and this is equal to a known velocity, subscript, comma, subscript, plus velocity of subscript, comma, subscript. All right, so this formula here helps us determine the velocities according to like whose perspective it's going to be. But the rule of thumb that we're going to use, and I'm going to use a different color ink, and I suggest that you do the same, is that this first subscript here and this subscript here have to be the same. Okay, and that makes this subscript here. Oops. Let's get a different color there. There we go. This subscript here and this subscript all the way back there, these are also the same. Okay, and that leaves us right here, this subscript here and this subscript here. Okay, these are what we call the cancel out subscripts, meaning that whatever subscripts we put there and there, we are going to be removing their perspective. All right, so that's the formula. Make sure you have that there. So let's try this one together. So if the question is, what is the velocity of C according to observer A? Okay, so if I were to use this formula, I would write VC comma A is equal to, and for now I'm just going to leave the blanks there so that we can add in the subscripts. Okay, so notice that here I'm going to do the same ones. The subscript here is C, and this one is also going to be C. Okay, and here this is subscript A, so the subscript here will also be A. Okay, and that leaves the unknown subscripts. Okay, so through the process of elimination, we can say that we are going to be using person B's perspective and while looking at person B. Okay, so when we do this mathematically, we know that VC of B, okay, we don't have that, but we actually do, because if we remember here, the rule is as long as you swap the subscripts, the signs just swap. So C comma B is equal to negative 0.3. So that'll be negative 0.3. And we have B comma A, which is negative 0.2. So if the question is how fast is person C looking like according to person A, okay, with the use of this formula, we see that VC of A is equal to negative 0.5.